The chain rule given capital F of x equal x squared plus 1 squared, and we want to find f prime of x. Now we don't have a formula for derivative of this. However, one can argue I can expand this out so that I can take derivative. Okay then, so what if you get f of x is equal square root of 1 over x plus 3, for example. So then truly we don't know how to take the derivative of this function. We know that f of x is a composite function. Capital F of x equal f of g of x. So in this case, g of x is equal 1 over x plus 3, and f of x is equal to square root of x. So how do we take derivative of the composite function? Note that the function g of x, taking the value from x, would mean the rate of change of x is g prime of x, or the derivative. Okay. In the next case, well, the composite function f of g of x taking the value g of x, then our rate of change is f prime of g of x. And what would that be? Okay. So we go from here. So here we get g prime of x, f prime of g of x. This combined together give you the derivative of a composite function is f prime of g of x times g prime of x. Let's go back to the problem that we have earlier. F of x equal x squared plus 1 squared, as f of x equal f of g of x. Here f of x equal x squared and g of x equal to x squared plus 1. Think about derivative of the composite function as you take in the derivative of the outer function, multiply with the derivative of the inner function. So here, the outer function is g of x squared, and the inner function is g of x equal x squared plus 1. So again, f prime of x equal to derivative of g of x squared. You're looking at 2 times g of x. The derivative of g of x is just 2x plus 1. And we know g of x equal x squared plus 1. So this is 2 times x squared plus 1 times 2x plus 1. So again, we take the derivative of the outer function, multiply with the derivative of the inner function. Take a look at this. If f of u is differentiable at the point u equal g of x, and g of x is differentiable at x, then the composite function f compose g is differentiable at x, and the derivative of f of g of x equal derivative of the outer function times derivative of the inner function. And in Leibniz notation, we have dy dx equal dy du times du dx, where dy du is evaluated at u equal g of x. So let's take a look at the derivative of the following. Let's first identify the outer function and inner function. Here's the outer function. Let's call the outer function f of x. F of x equal x to the 8. The inner function g of x is equal, the outer function f of x equal g of x to the 8. G of x is equal to 3x squared minus 4x plus 6. So take the derivative of the outer function. So y prime is equal g of x to the 7. So 3x squared minus 4x plus 6 to the 7 multiply with the derivative of the inner function 6x minus 4. Again, y prime here equal to times sine of x divided by 1 plus cosine of x. Derivative of the inner function. Let's simplify this. In the next one, here we have a product rule, and we also have the here we have the product rule, and we also have a composite function. So then y equal derivative of secant is secant times tangent derivative of square root of theta is equal 1 over root theta. So this is u, this is v. So here this is u prime times v plus derivative of tangent equal to secant square of 1 over theta. Derivative of 1 over theta equal negative 1 over theta square. So this is v prime. So this is 3. Go on to number 4. Y equal 3t times 2t squared minus 5 to the 4th. So y prime equal 3 times 2t squared minus 5 to the 4 plus 3t times 4 times 2t squared minus 5 to the 3rd times 4t. So this is 3 times 2t squared minus 5 to the 4th plus 48t times 2t squared minus 5 to the 3rd. Let's find the tangent line to the equation y equal 1 minus x divided by 1 plus x squared at x equals 0. So in order to find the tangent line, we need to find the slope. Okay. So first, our goal is to find the slope of the tangent line. Y prime at 0. So y prime simplify this. So y prime of 0 equal to, now y equal mx plus b. We have m equal to, we need to find what is y of 0. Y of 0 equal to negative 1. So negative 1 equal 2 times 0 plus b. B equal negative 1. So the equation of the tangent line at x equals 0 is y equal 2x minus 1. Suppose that a piston is moving straight up and down, and that its position at time t in second is given by the equation s equal a times cosine of 2 pi bt, with a and b being positive. A is the amplitude and b is the frequency. What effect does doubling the frequency has on the piston velocity and acceleration and jerk? So let's first talk about the frequency of this function. So s equal a cosine of 2 pi bt. The frequency is equal to 2 pi b divided by 2 pi. The frequency here is equal to b. So if we want to double the frequency, we are looking at 2b. Okay, so then the function now becomes s equal a cosine the 4 pi bt. So let's make this into two columns and see, so that we can make comparison. So s equal a cosine the 4 pi bt. And the original one, s equal a cosine of 2 pi bt. So what effect does it have on the velocity? Well, the velocity is the first derivative. So that will be negative a sine of 2 pi bt times 2 pi b. This will be equal to negative a sine 4 pi bt times 4 pi b. So look like it double on the velocity. Okay, let's see what happened with acceleration. But first, let's clean this up a little. Negative a 2 pi b times sine of 2 pi bt, negative a times 4 pi b times sine of 4 pi bt. Okay, so acceleration, that is the second derivative, that is we'll clean this up a little bit. And as the program here is and this is negative negative 16 ab pi times cosine of 4 pi bt. So note that what happened here. This is 4, this is 16, so it quadruple. So by doubling the frequency, the velocity then will go double and the acceleration will go quadruple.